Talk about those. Okay, strain, shear strain, result of force. Yeah, we got time. Result of force being applied to a material and deformation occurring. In other words, you've created this stress, and now your material's starting to deform. It's kind of like that pin that we said wasn't as big around as the diameter of the die holding the material, and all of a sudden it starts deforming and stretching. Okay, elongation, right? So that's what you're dealing with now. Notice, look at the shift in the planes on that example B. So that motor mount's sitting there, and all of a sudden you get some kind of a shear force applied, that P up there on the top, and the bolt's not failing, but it is starting to deform. Then that's shear strain. Note, it's a ratio of 2 lengths, therefore it's dimensionless, but it is expressed in terms of inches per inch or millimeters per millimeter when you start talking about strain. Now, strain, how do we calculate that? It's calculated as total deformation divided by the original length. So let's see if I can find my writing instrument here. There it is. So it's shown as epsilon is strain. That's probably not, that's more of a, see if I can find that to erase it now. Should be down here. Oh, I'm off the screen. Okay, let's go here. Eraser, I'll make that a little better this time maybe. That should have been like this. Epsilon is more like that. Is equal to the total deformation, and that's signified like so, good as I can do on this screen right now, divided by the original length. Okay? So keep that in mind as we go along here. And let's see. So they give an example problem there. It says calculate the total elongation or the deformation for a steel wire 60 feet in length if the strain is 0.00067 inches per inch. Well, the length L and the strain are given. So we've looked at this. So what are we given? We're given, okay, where'd it go? We're given this, which is the 0.00067 inches per inch, and we're given the length, which the original was 60 feet, right? So we need the deformation. So that is going to be rearranged to that right there, right? So if we do that, do what?
What problem is this?
It's at the bottom of 187, example problem 914. So it's 0.00067 inches per inch. I think it's probably best to write it like that. Times, and they're saying it's 60 feet, right? Well, we're dealing with inches. So it would be 60 times 12, wouldn't it? 60 feet times 12 inches per foot, right? So the feet cancel out, and you're left with inches. Okay, well, let's see, what does that do then? If you've got 12 inches at the top, and this is inches per inch, I can just find my cursor again. There it is. this inch goes away, and this inch down here goes away, and you're left with so many inches, right? Which, what's it come out to be? 0.84? 0.482? I said 84, didn't I? I still think there must be some dyslexia going on there. You know? Never was diagnosed, but that was before I got all that, before I could have been diagnosed. So what's that saying? If it's got that strain of 0.0067 inches per inch of strain on a 60-foot long steel wire, you can expect that it's going to stretch 0.482 inches with that much strain on it. That's all it's saying.
So
over the whole 60
the wire
inches.
would be 60 feet, almost 60 and a half feet, or 60 foot half inch.
Exactly.
Yeah. Okay.
Yeah. Yeah. What would the result of that be? Well, your wire would be 60 feet, 0.48 inches. Or yeah.
So it's not doing it perfect.
Almost 60 feet and 1/2 inch by with that pull on it.
Yeah.
Okay, and that's how a test problem might be phrased is, what's going to be my total length of this wire when we get done based on that strain and the original length. What could I possibly expect that thing to be at the end? Or a piece of rod. I've got a rod that's got, you could actually have one problem that would ask multiple things. I've got this rod that has a certain diameter. What's the stress on it? Okay, then what's the strain going to be based on that? If I'm given what the allowable would be, if you will, what the strain would be involved, how much is it going to change? And that's something that you might actually have to run into out in the real world. Kind of like some of you haven't had physics yet, right? But if excuse me, if you're dealing with the way things expand and contract, based on temperatures and such. So, but you've got to be given enough information to do that.
So your diameter would change because of necking too, or no? On a wire? Or
No, you wouldn't assume that.
Yeah, okay.
Because if the diameter starts changing, then you're starting to get close to that ultimate shear.
Okay.
Or actually, it's the next thing we talk about, which is, let's see, I think I got it here, where you got a stress strain curve. And what you'd be dealing with then, you get past that limit, the proportional increase in strain. You've got this limit here, the proportional limit known as Hooke's law, and then things start changing at that point.
Past that, the diameter.
Ultimate yield strength,
Yeah.
once you get past that, things go to pieces real quick, literally to pieces. And things fail. So, okay. Again, rearranging the equation, figuring out what you've got. You notice on these problems what I've been doing is I've been listing things that we've got. We know these values. We know what they are. We know this is a force. Okay, a force is signified by P. We know the area, it's signified by A. Where's my calculation? Where's my equation? And where do they fit in that equation? Then what am I ultimately looking for? Okay, start thinking in those terms and you'll be just fine. Because then it's just putting the numbers where they need to be and punching them in the calculator, isn't it? Again, what that guy had referred to as plug and chug all those years back. That's what it becomes. And that's what a lot of engineering type stuff is. Engineers, that's what they do all day long, is they go and find things that they need and plug them into different areas and make them work. So hopefully that's what you're looking forward to doing. If not, well, enough said about that. So that's the shear strain. Let's see, what do we want to talk about? Is there anything else I missed there on that? Not really. Okay, now the next thing we have to look at is the relationship between stress and strain. And that's this beast right here. Okay? For each increment of stress, there is a closely proportional increase in strain, provided a certain level of stress is not exceeded. If that stress exceeds that limit, the strain will no longer be proportional, and that's known as Hooke's law. So note over there on the right side, so if a bar is subjected to a tensile load, let's call it the force A, that produces a stress A and a strain A, then you subject that same bar to a stress B and a strain B, then plotting the results is going to result in a graph like you've got shown here. So you see the 2 points that they've plotted there based on the stress and the strain. And then if you connect those right through the zero location, if you will, or the origin of the X and Y axis, then you're going to have a straight line because it is a proportional relationship. Okay? That is known as the modulus of elasticity, or Young's modulus. And you'll have to use those numbers in some of your calculations as you start looking at different materials and such, okay, for the same types of bolts. Let's see, what else do we want to talk about that? But it is a constant relationship, so keep that in mind. Note says the standard tension test used to determine the modulus of elasticity was discussed in Chapter 10, along with the stress limitations within which modulus of elasticity is valid. So that's the next chapter. But the modulus of elasticity of steel is commonly assumed to be 29 million psi or 30 million psi in U.S. customary system. In the SI system, it's 20,000 megapascals, or excuse me, 200,000 or 200,007. Particular values depend on the type of steel. Purpose of this text, values of modulus elasticity for steel will be taken as 30 million psi or 207,000 megapascals. Note that when the values are shown in this form, the first number will be the value of the U.S. customary system, and the parenthetical value will be the SI system. So similar to our units when we're doing a drawing, if we have alternate units shown, you'd have English units first and then the metric. It's the same thing on this.
So they're just grouping all kinds of steel together and giving you one generic.
Yeah, kind of. It's probably like a 1020, that 1020 steel we were just talking about. It's probably for that. But yeah, that's kind of a generic. That's pretty scary, isn't it?
Well, yeah, I mean,
Because there are many different steels and many different alloys and so on. So yeah, and I don't know, do we actually have any information like that in the back of the book?
Everybody has their 140 book. I remember it being there. I just don't have my own.
Do what?
They're in the. I know they're in our one. Or
engineering material.
Oh, yeah.
140. Oh, that's there in this one.
I don't see anything. The
G.
G?
That's what it says in the paragraph.
Yeah, okay. So there's your different steels, Al. Steel with the different alloys. And AISI 1020 hot rolled, notice they've got but the modulus of elasticity for all of those is very similar. 30,000, but that says 30,000, but be careful, that's 30,000 kips per square inch, which would be, you'd have to put three more zeros on that, right? Because it's 1,000. So you have to be able to make. it ends up being 30 million, yes. Yeah. And I think the reason they can do that, Al, is because if you really went back and broke each one of those out, the change in those is probably so insignificant. You know, it's like, well, in the case exactly in there, I mean, it's assumed to be 29 million, so we're just going to round it up to 30.
All right. 'Cause
You know, so one of them might be 29,200,000 or something like that, and the next one might be 29,100,000. So we're just going to make them all 20, but we'll make them 30 million. But what does that do then? That probably adds strength, doesn't it? It means it's going to take more to break that, to make it fail. So, yeah, I think that's why they can go generic on that. Note, though, that some of the different values there for modulus of elasticity, that aluminum, you know, is quite a bit, what? Haven't you always heard aluminum or steel is 3 times stronger than aluminum? But aluminum's lighter weight, right? Well, right there is the reason. Look at the modulus of elasticity of aluminum. It's a third of the modulus of elasticity of steel. So that's our case in point. But then you go down and look at magnesium. What's it? Holy cow. Sucks, doesn't it? Okay, but
Better than concrete.
you know, better than concrete. Well, concrete doesn't. Yeah, it does have a modulus of elasticity. Yeah, it's twice as good. Okay. What else on that? I think that.
It says copper hard drawn. What's hard drawn?
Copper hard drawn as opposed to. Oh, you're
That's
getting
the
into
copper.
you're getting into your materials class now. That's one to ask Ucker, isn't it?
I guess, yeah.
Copper hard drawn, yeah, as opposed to what? I don't know. I mean, the drawing process is where you're pulling it through a die. So yeah, it's an extruder. You're actually pushing it through. I don't know if that means they heat it up to make it soft or what. I don't. Guess I'm not. I can't answer that.
Going back to what you were saying about the different values at the top, there's even a note that says that the values are approximate and only provided solely for the specs. So it could be, the high strength low alloy is actually over 30,000, but they just reduced it so it's just one common number. That might have been the reason why.
Yep.
They haven't.
Well, and I suspect if you looked at any book, it's going to say the same thing.
Right.
You know, they just.
Without a machinist handbook, you can't really.
Yeah, don't go out in the field and reference your textbook, basically.
Yeah. Go to the manufacturer that is supplying you the material, and look for all their numbers. Okay. Don't. That's where you've got to look when you're dealing with a particular vendor. And then you have to, basically, you're at their will, aren't you? That if they supply you engineering data, and this happens too, doesn't it? I mean, especially if you're going from, let's say you're basing everything on bolts that were maybe made in America, and then you get some Chinese bolts, and the engineering data wasn't really what it was supposed to be, and you get failure. I mean, that's happening out in the real world. It's just the way it is. I'm not trying to pick on the Chinese, but somebody's fudging the numbers, and you get caught. Now you're on the hook too.
Kind of why they use a safety factor of 2 or 3 in every.
Yeah, but even at that, I mean, you still could be hung out. I mean, yeah, that's
I mean, at least it's somewhat of a protection, just saying,
right.
oh yeah, go right to 1 and 3/8.
Well, but then, and likewise, I mean, just like with the ladder, how many times have you looked at the ladder and said, well, it says it's only rated for 200 pounds. Well, I know I'm more than 200 pounds and I get up on that ladder. But in reality, it's probably rated for 400 pounds, but they're telling you 200 because they know you're going to exceed that. Brian?
Yeah, for aviation
Yeah,
Right, in,
Yeah.
in light, and, I mean, in critical situations,
yeah,
and hardware's, I don't know how many times over the strength.
right. And but that's a whole different deal. I mean, we have to account with, in the engineering design phase of it, we have to trust that that manufacturer is giving us the right information based on, what their charts say. We have to trust that that's true. That's not always the case. I mean, in your case, they're actually supplying or they're exchanging a bolt that we said had to be there. They're changing our design, making it much less or much more inferior. Okay, they're taking a hardened bolt and supplying just a regular garden variety out of the hardware store, Home Depot bolt in a jet engine. It's not good. So, but that wouldn't be the engineering department's fault as much as the people putting it together. But as engineering type folks, we're going to have to trust that manufacturer's data. So there's just no way around that. But like I said, when you get the machine design, they'll tell you bump that factor up just partially for that reason. Especially nowadays. Back in a different time, it wasn't so much like that. There wasn't all this cutting corners and such to make it more profitable. So, hey, I didn't look over what problems I'm going to assign you, so I will do that and post them on Blackboard. Okay, and